All right. So what we were talking about before all this tests and beam design and slab design stuff, started occupying your minds. We were still pressing on with material, and we were talking about flanged sections, primarily T-beams. Now, a T-beam versus an L-beam versus, let's say, a box beam is really no different. It's just a function of the system that you're looking at and the geometry. But in the end, a flanged section really presents the same analysis problem regardless if it's a T-beam, L-beam, what have you. Now, for this class, because we're primarily interested in building construction and the layouts of composite floor systems and what have you, when I talk about T-beams, what I'm really talking about is sort of a ribbed slab system. So I have a floor slab that is ribbed with flexural beams, every so on and so forth, to resist bending moments and shears. Now, what we'll do in a T-beam analysis is the first thing that we need to do is assess how much of that slab is effective for a given beam. And the reason why that's important is because when you're looking at a T-beam, when you're looking at something like that, the problem is that those flexural stresses inside the slab, they tend to dissipate the farther you get away from the beam. So you have to sort of say, okay, that's the amount of beam that we're going to consider. Now, in the bridge spec, they actually keep it a lot simpler. They just say tributary width, halfway over, halfway over. We don't do that in building design. We have a pretty straightforward plug-and-chug expression to compute the provisions for T-beams and L-beams. It's literally a plug-and-chug expression, just the minimum of those values. In the end, I think it's pretty straightforward. One thing to point out, it is a different expression from T-beams to L-beams because your assumed stress profile is a little different on the end than it is for some generic beam in the middle. Okay, the added complication, though, with T-beams, where it really gets funky, is when you have to assess whether or not you're dealing with a rectangular T-beam or a true T-beam. Now, a rectangular T-beam is such that the stress block is in the flange. And if you look at this, it's really no different than what we've been doing before. Just a rectangular beam, steel in the bottom. It's no different because the stress block is rectangular just like it was before. This, however, is what we call a true T-beam. True T-beams are different because their stress blocks are in the web as well, and now the stress block is truly T-shaped. So the capacity calcs for something like this are way different than for something like that. So we had two examples that we were looking at. The first one that we did was rectangular in nature, and I'll just go ahead and tell you this one will be a T-beam or a true T-beam. But I do want to take some time, excuse me, and at least review some of the math that we did for the first example. All right, so we were somewhere about right here. Yeah. I guess I should be, put that and call that 8A, be consistent. So this is example 8A. The first thing that we did actually is we just, used the parameters of the example, what was given to us, and actually just drew out the floor system and made sure that we understood what was going on. So these were all the dimensions that were given, and from that we were able to interpret things like what's the center-to-center girder spacing and what have you. Now, what we really cared about, though, was this effective flange width, this B value, which, again, plug and chug for a T-beam. Minimum of these three quantities, plug and chug, and you get 60 inches. Now, the first thing that you have to do when you're analyzing a rectangular T-beam, trying to figure out how much this beam can hold up before it's going to fail, is you have to determine the depth of your neutral axis. So the first thing that I did is I said, well, 0.85 FC prime times the area in compression has to equal the force in tension. C equals T. So the area in compression, in order to maintain equilibrium, has got to be about 106 square inches. Okay? Now, that's how much we have to have in compression. The flange, just the width times the thickness of this rectangular portion up here, Well, its area is like 240 square inches. So because of that, the stress block looks something about like that, and we are dealing with a rectangular T-beam. This problem is analyzed no differently than the stuff we've done before. What's A, 0.85, or ASFY over 0.85 FC prime B? Plug and chug, and you get 0.765 inches, or 1.765 inches, which makes sense because the flange depth is 4 inches. So that neutral axis has got to be less than 4 inches. Mn, ASFY d minus A over 2, we get a moment capacity of about 693.5. Now we don't care about Mn, we care about phi Mn. What is phi? Say it louder. It depends. It depends on what the strain in the steel is. Okay? Well, that's because we did the determination. All right? Now, so we calculate the depth of our neutral axis C, A over beta 1. So that comes out to be just over 2 inches. Strain in the steel, 0.003 D minus C over C. It is greatly larger than 0.005, so phi is 0.9 for this example. And again, for most examples, it will be 0.9, but the big message is that phi, what is phi? It depends. So phi Mn is about 624 foot kip. So this was our nominal capacity. We've adjusted it for design purposes. Any questions? Okay. Excuse me. So now let's look at example 8b. No, that's not 70. Greater than or equal to. Sorry. All right. Okay, now a couple things. So here's example 8b. Let's sort of, take stock of it. Now I've given you a couple of values that normally you'd have to compute. Like example 8a, we had to determine what is the effective flange width. I just told you B is 30 inches. I told you, that because I just wanted to move through this. The idea, though, we want to determine what's the capacity of this section. So we're going to take the same approach that we did last time, but we're going to see a different result. Okay? So same approach. All right? So example 8b. So to start off, close enough, we can start drawing in some of these dimensions. So we know, for instance, we know that that dimension is the web width, and it is what? You all have it in front of you. There we go. All right. Let's see. This is the height of the flange, and it is what? 4 inches. There's going to be some steel here. Now this is D, and it's what, 30 inches? And as for the steel, there's going to be something about like that, right? And what's the area of steel? It's like 10.12 inches squared. So there's that. And let's see, we've got this dimension is B is 30 inches. All right. And we also know that FC prime is 4 KSI FY 60 KSI. Right? All right. Any questions? Okay. Now, so I'm going to approach this the same as before. We're going to determine the location of the neutral axis. So And what principle do I use to determine that location? Equilibrium. In other words, that the compressive force has to equal the tensile force. So here's how I'm going to do this. I'm going to do it the same way I did before. That 0.85 FC prime times whatever the area in compression is has got to equal the area in tension, which is, or the force in tension, AS Fy. So whatever compressive force we have, that must equal our tensile force. So therefore, our area in compression has got to equal 0.85 FC prime all under AS Fy. So plug and chug, we've got 60 KSI. Oh, I'm doing it backwards, but maybe I'll be consistent. 10.12 inches squared times 60 KSI over 0.85 times 4 KSI. All right. Plug and chug, and that gives me what? Nobody brought their calculator? Goodness. Making you all wake up. I know it's Monday, but it's like 10:30. You should be awake. Oh. All right. Is anybody getting this? Anybody getting that? What? 178.59, something about like that. Now, what is the area of the flange? There we go. It's B times HF, which is 30 inches. Right? Make sense? So that means what? We're dealing with a true T-beam, right? So I'm going to draw some sort of symbolic dimensions and see what we can get with this. All right, so therefore, NA is in the web, and we're dealing with a true T-beam. So let's just look at this for a second. So here's my beam. All right? And by looking at this, you're saying the stress block has to look something about like this. So the stress block has to go down in here because there's not enough area in the flange to maintain equilibrium. Make sense? All right. So what we're trying to find really is this depth right here. And what do we call this depth? When somebody said C, it's not C. It's A. Okay. Now this dimension is B. This dimension is HF. And this dimension is BW. Does that make sense? All right. Now, what I'm going to do over here on the right is looking at this, schematic that I've got here. Let's draw out the area in compression. Let's see if we can derive it. Okay? I propose to you that the area in compression, let's look at it like this. Let's cut this into two separate rectangles. The area up top is what? B times HF, right? On the bottom, it's BW times what? There we go. There we go. Does that make sense? So now we can solve for A. Now, one thing I will say to sort of simplify this is what is BHF? That's the area of the flange. Because I'm lazy, I'm going to copy this. All right. Everybody good? Can I go ahead and switch? Hold on. What would you all do without iPhones? I mean, goodness. Here, should I, pose? You lost your chance. The videos are posted. Oh, man. That was a good comeback. That was a good comeback. All right. So, is everybody okay with this expression right here? Everybody okay with this? So, what I'm going to do is solve now for A. So, what do? Okay, I subtract this over here. So, hold on. There we go. So, if I subtract, I get A compression minus A flange equals BWA minus HF. And then what do I have to do? I just have to, divide both sides by B sub W. And then if I'm solving for A, add that over, right? So would a fair expression be, therefore, A is the area in compression minus the area of the flange over BW plus that. Is that a fair expression? So let's see. What was the area in compression? What was that? There we go. Making sure y'all paying attention. Minus 120 over the web width, which is, what is it for this problem? There we go. Plus 4 inches. Plug and chug, and that will be 8.185 inches. Not too bad, right? Now, obviously, this is greater than 4 inches, so that validates our assumption. And you go, well, wait a minute, you're adding 4, so obviously it's going to be 4. Well, if you did some incorrect math, this would come out to be negative, so it's just side point. Now, everybody good so far? Okay, what I'm going to go ahead and do right now, just so that we have it, I'm going to go ahead and determine feet. because what I'm about to show you and how I compute the moment capacity might be a little different, so I want to make sure that we're fine with this. Okay, so how do I determine phi? What's the first thing I need? No. I don't need that for phi. You're talking about phi mn. I'm talking about just phi. Phi is based on what? What's phi based on? The strain in the steel. So I calculate the strain in the steel by saying 0.003 d minus c over c. What do I need? Well, I've got d. I need c. How do I calculate that neutral axis depth? I take a... What? No. I take a over beta 1. A is 8.185 inches over 0.85, and that's 9.629. I mean, are you all right with this? I mean, I know it's Monday, but I mean, we were just looking at that, so for 4 KSI concrete. What's that? It's your table in your notes. It's also in the book. Whatever. Is everybody okay with what we're doing? If I got to do the, I will. Okay. So now that I've got C, I can calculate the strain in the steel, 0.003 D minus C over C, which is 0.003. What is D for this problem? 30 inches minus 0.629. And then that's what? Make y'all do some math this morning. Huh? Excuse me. Yeah, that's what I got. I got like 635. So what does that mean? Phi is, and it's 0.9 because this is 0.005. Greater than or equal to 0.005. I was making fun of myself there. All right. This next part's where I'm going to need y'all to really pay attention. Yes, you are, most certainly.
If we got 0.00495,
You're probably, if it's like 0.499, you're going to probably end up rounding your phi anyways, and it's probably going to end up being 0.9, so that's fine. Let's just put like, if we're talking about homeworks and exams and things like that, that shouldn't happen if you do the problem correctly. As an engineering judgment question, I mean, depending on the number, it's close enough, you know. All right, has everybody got what's on the screen right now? Because next part, I want y'all paying attention. Everybody good? All right. Now, I know that what we're doing is employing a lot of, concrete-related principles, Whitney stress block, all these strain limits and what have you. But in the end, we are dealing with equilibrium. We calculate our depth based on force equilibrium. The sum of forces in one direction must equal the sum of forces in the opposite direction, right? All right. When we did our moment expression before, remember ASFY and then times D minus A over 2, how did we come up with that? It was force times a moment arm, right? That's it, okay? Force times a moment arm, okay? All right. So we're going to do our nominal moment capacity. And I'm gonna make a couple points. So recall, our nominal moment capacity before was what? Some force times some moment arm, right? We're going to use that very, philosophy. But let's recall what we did before. Before we had a rectangular beam, right? We said our force was ASFY and our moment arm was D minus A over 2. So we were summing moments about the center of the stress block, right? What I'm going to do here is I'm going to sum moments. Here, I'll write this down. We'll sum moments about the area of steel. Okay? Now, you'll see why I'm doing this, but I'm, in the not too distant future, but I'm also going to split this up a little differently. I'm going to turn this into 2 rectangular beams. You'll see what I'm going to do. So, would you agree with me that what we're dealing with is a beam that looks like this? We've got steel. I don't know how many bars, it doesn't really matter. That looks something like this. And this stress block is proportioned such that the area of this stress block will generate the same compressive force as this steel reinforcement will, right? I'm going to split this up into 2 different beams. I'm going to say that this equals the following beam. And just give me a moment to draw all this out. With a stress block that looks something about like this. Plus this beam. Let's say we got a little bit of steel here and a little bit of steel here. Okay. So what I have done is I've said that this stress block is going to be split into the contribution from this one and the contribution from this one. Everybody all right with that? Let's put a little bit of dimension on our stress blocks. You all help me out with this. What is this dimension right here called? A, that's A. This dimension. BW. Everybody okay with that? What about this dimension? What is this dimension right here called? HF. All right? Now, let's look at this one. How wide is that? Whoop. All right, 1/2 B minus BW. Exactly right. Does everybody else understand that? Everybody okay with that? Now, reason why I've split this up into these 2 components is because I'm going to call this first one the web couple, and I'm going to call this the flange couple. You're going to like this. It's going to be kind of nifty. Everybody okay with what I've got so far? Now, let's start computing some forces, okay? So I want you to tell me what is the compressive force generated by that web couple. How would you calculate it? The compressive force. In other words, what's the compressive force generated by this? It's concrete in compression, so what's my stress? There we go, 0.85 times the area. What is the area? There we go. You said that, right? Okay. All right. ABW. The width of the web. All right. Plug and chug. What do we got? 0.85 times, what's FC prime? There we go. What's A? There we go. And this is 14. Plug and chug, and you'll get like 389.6. All right? Bless you. Now, C sub F, the flange force. What is, let's work that out. It's 0.85 FC prime times what? Times what? Width times thickness times H sub F, right? So both of the, so really what I need is 0.85 FC prime times the area of each of these. Now, in terms of width, I got half here, half there. So why don't I say the width of the whole thing is just B minus BW? And why don't I say the thickness is H sub F? So how about this as an area? H sub F, B minus BW. How about that? Is that a fair statement? Now, 0.85 for KSI. What's the flange height? And what's B? B is what, 30 inches? Minus what? 14 inches. Excuse me. Plug and chug, and that will give you 217.6 kips. Is everybody okay with that? Okay. Now, those are forces generated by this beam in compression. What is the tensile force generated by this beam? We're not going to use this. This is just for a note to make. The tensile force is correct, ASFY, which is 10.12 inches squared times 60 KSI, which is what? .607.2. What happens if you take these two compressive forces and add them? What do you get? Compression equals tension. That's a check what we're doing's right? So the tensile force ASFY is 607.2 kips, and if you actually add C sub W plus C sub F, you get 607.2 kips. So this is a check to see what you're doing is correct. Now, before we advance to the next slide, I do want to have a little bit of discussion right here, and I might even box this in so that you all can see it separate from everything else. I'm going to call this moment arms. Remember, we're calculating a force times a distance, right? Now, our moment arms are the distance from the center of this steel, wherever it is, to the center of this compressive force. Keep in mind our dimension, this dimension here, that's D. This dimension here, that's D. Okay? So, help me out. How far is it? Let's look at the web one first. How far is it from the center of this force to the centroid of that force? Nope, not A, close. D minus A over 2. Now, if that's the case for this force, what about that one, the flange couple? There we go. Make sense? I'll give you all a moment to catch up. Does everybody understand that? We're going from the centroid of each individual shape. And we're going to chug this one out and we're going to call it. So, everybody good? I'm going to skip to the next one if everybody's good. So therefore, I propose to you that Mn is not ASFYD minus A over 2. I propose to you that it's CW times D minus A over 2 plus C sub F D minus HF over 2. So that's 389.6. And then D is 30 inches minus 8.185 inches over 2 plus C sub F is 217.6. And then 30 minus 4. You plug and chug that, you're going to get, let's see, what is that? It's 16186.4. That's just taking those numbers, plugging them straight into a calculator. What are the units? Inch kips. If I take that and then multiply it by 1 over 12, I get 1348.9, and then recall, what's phi for this problem going to be since we've already determined it? See why I went ahead and did that earlier? Phi Mn is now, did that answer your question, Mr. Yukonik, earlier about what's the difference between rectangular and true and how do you determine that? Because you asked that a little while ago. What? We haven't gotten to that yet. And that's, let me say this, rebar in the compression region is something that you need to be able to assess, but it's different. It's another topic in and of itself. We will handle that, but not right now. Is everybody good with this? All right, that's all I've got for you all today. We're going to do T-beam design next time, so we do press on. All right, we'll see you.